Dr. Ivo Bolsens. Ivo joined Xilinx in 2001 as a Senior Vice President and CTO. He's responsible for identifying Xilinx's future technology and talent, as well as heading up the Xilinx Research Laboratories, which focuses on advanced development in the areas of silicon, systems, and software. Dr. Bolsens came to Xilinx from the Belgium-based research center, IMAC, where he was the Vice President of Systems Research and Development. Bolsens earned his PhD in electrical engineering from the Catholic University of Leuven in Belgium. He is author and co-author of more than 100 papers in the field of SoC design, EDA tools, embedded software, and wireless communication. So without further ado, ladies and gentlemen, please help me to welcome Dr. Ivo Bolsens.
All right, good afternoon. I'm going to try to give you a little bit of an insight, in what AI and machine learning means for the semiconductor industry and, what direction that we are heading. And to start off, I would like to start with a quote from a European writer more than a century ago. He said at a certain moment, it's the best of times, it's the worst of times, it's an age of wisdom, and it's an age of foolishness. And to a certain extent, you can refer to that also when you think about where we are today in semiconductor technology. When you look at the negative side of that, people would be worried about the slowing down of Moore's law, and traditional programmable architectures are not giving you any more the merits that you had in the past. Now, when you have a more positive view, you would refer to what many people quote as Kurzweil's law, which basically is the law of accelerating return of technology. And basically, there, Kurzweil states that Moore's law is just an episode in the evolution of technology and the return of the benefit we get from technology moving forward. He claims that the exponential growth of the benefit we get from technology in computing has been going on for more than a century. Moore's law is just one episode in that, and as Moore's law is slowing down, we will see new technologies and new capabilities that will move forward, the front end of technology and the front end of computing. And so you can look at this in a positive and a negative way, but I would say that, definitely I'm looking at it at the positive side, because I think it has never been such an exciting time as long since I've been around in the semiconductor industry than it is today. There's a lot more opportunities now to innovate, and of course people will continue to try to scale. Scaling will slow down somewhat, but there is many more dimensions, and some of them literally the 3D dimensions, that will help us to continue to improve the compute capabilities of our semiconductor products. And today I would mainly, highlight a little bit the component, which is probably the most disruptive and the most exciting component, which is the breakout of new compute architectures, which I will refer to as domain-specific architectures. And of course, as previous speakers have been alluding to, a lot of that has been driven by some of the mega trends that we see in the industry, right? Everybody here in the room, understands that, big data is happening, and it gives rise to, the evolution of a humongous cloud infrastructure, you know, to enable us to deal with the volume, you know, the velocity and the variability of the data that is being generated by all the devices that are connected to the internet and the people that are connected to the internet. And then the 5G wireless that will allow us to add mobility and higher bandwidth and flexibility. IoT, which is another major trend coming towards us. And then finally, the evolution of the autonomous driving cars that is ahead of us. Now, one of the foundational aspects of this megatrends is that a lot of it is relying on artificial intelligence technology and specifically on machine learning technology. So, referring to some of the previous speakers, you know, AI is definitely not a hype. AI is there to stay. From now on, we have gone through a few AI wins in the past. I think we have reached now the capability of really living up to the merits and the promises that are coming towards us from AI and machine learning technology. Now, another important aspect that is driving, you know, the evolution and the penetration of machine learning and artificial intelligence is the introduction of much more computing, you know, at the edge of the network. Whereas a lot of people, you know, probably have seen applications of machine learning, you know, that are running in the cloud, in the infrastructure. As machine learning and AI is penetrating more and more in our day-to-day lives, it will also, you know, show up in a lot of the compute capabilities that are much closer to the home, literally. And that's what we refer to as edge computing. Now, the interesting thing is that whereas, you know, all of this, you can kind of capture that as machine learning and AI, the merits of these different functionalities, be it in the edge or in the cloud, are different. When you have, you know, AI and machine learning deployed in the edge, you typically will measure the merits of these infrastructure by its real-time behavior. You deploy things in the edge because you want to have instant behavior. Contrary to the cloud, where you typically want things to run as fast as possible. In the edge, you don't want that, because if they run too fast, it means you're wasting power. It means you're wasting potentially resources. You're wasting money. You're wasting size and volume. So you want it to be just in time, which is real time. Different than in the cloud, which requires that your architecture might be different for deploying machine learning in the edge and deploying machine learning in the cloud. Also, you want to be the behavior in the edge for many of the applications to be deterministic. You want to be sure that whenever you execute a certain function, it is guaranteed always to behave at the same way. When you hit your brake pedal or your car, you want it always to behave exactly the same way. You don't want to have a challenge that it happens to be, you know, that your brake is a little bit later now because there was another function running, you know, on that hardware. So determinism in the edge is a very important criteria that will imply potential different architectures. Power consumption and latency are also new figures of merit that are different than what you traditionally see in deploying applications in the cloud. So now next to that, when you think about machine learning, it's interesting, you know, when you try to explain to people what machine learning is all about, it's like solving a compute problem without really designing a specific algorithm to solve your problem. What you basically do is you're applying a lot of test data to your neural network or your network, and you tune it in such a way that for all the test data, it gives you the right answer. And you basically expect that then the next time, it will also give the right answer. I asked recently one of our partners that is working on autonomous driving, how do you know that the car, will make the right conclusion the next time it has to make a decision? And the answer was pretty scary. It was like, well, because it did the previous times. So it is definitely an interesting way of thinking about it. But what's important about this to realize is that when you think about machine learning, there are two components in it. First of all, there's the training component, which requires completely different compute than what the second part is, which is the inference, which is the deployment of your application. The training is basically setting up your compute in a way that when you deploy it, it will behave in the right way. And to give you an idea, training is a tremendous amount of compute. If you think about a specific, for example, image qualification network, an image database like ImageNet, which is 1.2 training images, you have about 28 billion calculations you have to do per image. You have 1.2 images. For each image, you have to do about 100,000 of these iterations before you finally, over these 1.2 million images, have come to a conclusion how your network should be trained. Now, I don't know about you, but I once did a calculation. That's about a number with 20 zeros, more than 20 zeros behind that number in terms of number of calculations. And I looked it up. That's referred to as sextrillion type of calculations. I don't even can imagine what that means, but it's a tremendous amount of calculations. Inference, on the other hand, is a little bit less compute intensive, although it still requires, billions and billions of operations to come to one conclusion. So the message here is this is a very compute intensive activity and different for training and inference. Now, of course, because inference relates to the deployment of your application, the growth for the need of hardware that covers inference is much larger than training, because training, you basically will do that for one application, whereas for inference, you will deploy it, in many instances. And so the expectation is in terms of driving, the semiconductor growth that is backed up by the need for machine learning capabilities, it will be mainly driven by inference. So now when you start thinking about building architectures, that deal with the kind of workloads and the uniqueness of these workloads that I was talking about, there are a few challenges. Some of the challenges, of course, that we are just at the beginning, of the deployment of AI, and there is a lot of research, academic work going on, so the innovation cycle is going at a very fast pace. The figures of merit, which for traditional compute always were like teraops per second or gigaops per second of clock speeds or that kind of numbers, these become less relevant, and it's more about what's the latency. How long does it take before I get an answer? What's the power consumption? And also, is my hope. Typically, machine learning and AI is part of an overall functionality. It's not just something that stands on itself. When you deal with a car, you have to first, interpret a lot of these sensors. I mean, the future cars will have at least, 20 to 30 sensors in there, from cameras to lidars to sonars to radars, you name it. And you have to bring all that data in a consistent way together. So, the message here is, we are in an early stage of machine learning. There's a lot going on, many applications, many different approaches, and some of these acronyms, CNNs, RNNs, LSTMs, MLPs, you better get familiar with them, and there are more to come, right? There's a lot of innovation happening in this world, driven by different applications. Just to give you an idea of what happened in the last couple of years, if you look at one specific problem, like image classification, I mean, looking at an image and deciding whether it's a dog or a cat that you see, for example. I mean, the amount of neural networks or different topologies of networks that are dealing with that problem is exponentially growing, right? So that's an indication in how fast, you know, the innovation is happening. The other aspect is this, as this innovation is happening, when you think about semiconductor cycles, we have the cycle of the semiconductor where you start by your design and then you finally get into production. Now you can easily, by the time you have started your design to when your chip is in production, you have gone through several generations of new neural networks, new technologies, new inventions that basically are breakout compared to when you started. So there is a challenge there in the match of the timelines. So another important aspect is latency. You know, we all know that one of the drivers for machine learning is automotive, and you can imagine, you know, that latency, when you hit the brake, or when the car decides to hit the brake, it has to make that decision pretty quickly. So latency is important. And so it's not just about how fast you can produce or consume your data and produce results, but it's, you know, how long it takes, you know, between producing the results and reading the inputs. And there are different architectures. Okay. Looks like the beeper is stuck, I think. Here it's doing well, but not on the screen. Let's just do the next slide. Okay, so here you see an example of where you have an architecture that can generate, you know, high bandwidth, but that has to collect the inputs before, a whole bunch of inputs before it generates results. We talk about batching. Some of the previous speakers were talking about that. So you can have another architecture that has the same, you know, capability in terms of processing the data, but that can generate data, you know, output data much faster. So that's the impact of what an architecture that has potentially the same compute capability, but has a different latency. So you have to think about these challenges. You also have to realize is that power in many of the edge applications is important. So power consumption is important. Therefore, you have to really be careful about thinking about your arithmetic. Now, one of the interesting things about machine learning is that you don't need high accuracy arithmetic. So your compute can be, you know, 4-bit additions, 2-bit additions. You know, you can change your arithmetic dramatically depending on your application, and your architecture should be able to cope with that. So ultimately, what you need is hardware that can deal with the innovation cycle, that can deal with the new challenges, and that can be adaptable to, you know, the flow of the data, the topology of your networks, the hierarchy of your memories, and the precision that your arithmetic needs, and you can customize your architecture for that. And so, if you look at that kind of architecture, so in Xilinx, for example, we have the product that we refer to as Versal. And if you look intrinsically what that architecture is about, it is a very heterogeneous architecture because it has to cope with all these multiple requirements that are very different, whether you're talking about edge or whether you're talking about cloud, whether you're talking about, you know, latency-sensitive applications or power-sensitive applications. It's heterogeneous. It implies a lot of parallelism, it's scalable, and it is programmable. So if you look at that architecture, what you see, it's typically composed out of traditional compute architectures, which we refer to as scalar engines, in this specific case, ARM processors. It constitutes out of programmable logic and programmable memory, which is a more traditional FPGA architecture. And it consists out of, you know, a large array of compute engines, vector machines, which are typically being deployed in many of the machine learning applications. So that's how these architectures look like. Now the challenge, of course, you have is how do you program that, and how does the software stack look like that you are, building on top of these? Because this is definitely a very challenging architecture to be able to program. So you need to be able to have an architecture that, of course, is accessible to software people, and that can evolve and can allow you to do very rapid deployment of your applications. And so that's why also what you start seeing in the semiconductor companies, a lot of effort being spent on bridging that gap between that very high performance hardware and then the software, which is typically manipulated by data scientists who have not necessarily all the insights in the details of the architecture. And a lot of investments are happening in the semiconductor companies right now, and also startups have to invest a lot in software and not just in the architecture. It includes the connection with frameworks, dealing with open source and customer network models. It deals with dedicated arithmetic libraries. It deals with compiler optimizations, runtime optimizations, and then dealing with different underlying architectures of the hardware. So these are some of the challenges that are coming towards us in the semiconductor industry, but these are also opportunities driven definitely by the deployment of artificial intelligence in a lot of applications that will introduce more ambient intelligence in our world, which becomes pervasive for many of us. So thank you.
Thank you, Dr. Bolsen. This is from the leader of the CTO of the leading FPGA companies in the world. Thank you. Today we are very honored to have not one but two speakers with European origin. So, the technical stuff aside, just so we can get to know you on a personal level. Which country in Europe produce the best chocolate?
Well, some of you might know that I'm from Belgium, so. And by the way, the best beer too.
Thank you. So we have our incoming president, Denny, to share the flag and follow up with Dr. Bolsen.